Ozone, or trioxygen, is an inorganic molecule with the chemical formula O, I1/4O, or O3. It is a pale blue gas with a distinctively pungent smell. It is an allotrope of oxygen that is much less stable than the diatomic allotrope O2, breaking down in the lower atmosphere to normal dioxygen. Ozone is formed from dioxygen by the action of ultraviolet light and also atmospheric electrical discharges, and is present in low concentrations throughout the Earth's atmosphere. In total, ozone makes up only 0.6 ppm of the atmosphere. Ozone's odor is sharp, reminiscent of chlorine, and detectable by many people at concentrations of as little as 10 ppb in air. Ozone's O3 formula was determined in 1865. The molecule was later proven to have a bent structure and to be diamagnetic. In standard conditions, ozone is a pale blue gas that condenses at progressively cryogenic temperatures to a dark blue liquid and finally a violet-black solid. Ozone's instability with regard to more common dioxygen is such that both concentrated gas and liquid ozone may decompose explosively. It is therefore used commercially only in low concentrations. Ozone is a powerful oxidant and has many industrial and consumer applications related to oxidation. This same high oxidizing potential, however, causes ozone to damage mucous and respiratory tissues in animals, and also tissues in plants, above concentrations of about 100 ppb. This makes ozone a potent respiratory hazard and pollutant near ground level. However, the so-called ozone layer is beneficial, preventing damaging ultraviolet light from reaching the Earth's surface, to the benefit of both plants and animals. Nomenclature: the trivial name ozone is the most commonly used and preferred IUPAC name. The systematic names 1I1, 3I1 trioxidane and I1/4-oxidodioxygen, valid IUPAC names, are constructed according to the substitutive and additive nomenclatures, respectively. The name ozone derives from ozane, the Greek word for smell, referring to ozone's distinctive smell. In appropriate contexts, ozone can be viewed as trioxidane with 2 hydrogen atoms removed, and as such, trioxidanilidine may be used as a context-specific systematic name, according to substitutive nomenclature. By default, these names pay no regard to the radicality of the ozone molecule. In even more specific context, this can also name the non-radical singlet ground state, whereas the diradical state is named trioxidanediol. Trioxidanediol is used, non-systematically, to refer to the substituent group. Care should be taken to avoid confusing the name of the group for the context-specific name for ozone given above. History: ozone, the first allotrope of any chemical element to be recognized, was proposed as a distinct chemical substance by Christian Friedrich Schaparrograph NBEIN in 1840, who named it after the Greek verb ozane, from the peculiar odor in lightning storms. The formula for ozone, O3, was not determined until 1865 by Jacques-Louis Sauret and confirmed by Schaparrograph NBEIN in 1867. For much of the second half of the 19th century and well into the 20th, ozone was considered a healthy component of the environment by naturalists and health seekers. The city of Beaumont in California had as its official slogan Beaumont, Zone of Ozone, as evidenced on postcards and Chamber of Commerce letterhead. Naturalists working outdoors often considered the higher elevations beneficial because of their ozone content. There is quite a different atmosphere, at higher elevation with enough ozone to sustain the necessary energy, to work, wrote naturalist Henry Henshaw, working in Hawaii. Seaside air was considered to be healthy because of its ozone content, but the smell giving rise to this belief is in reality that of rotting seaweed. Physical properties: ozone is colorless or slightly bluish gas, slightly soluble in water and much more soluble in inert non-polar solvents such as carbon tetrachloride or fluorocarbons, where it forms a blue solution. At 161 K, it condenses to form a dark blue liquid. It is dangerous to allow this liquid to warm to its boiling point, because both concentrated gaseous ozone and liquid ozone can detonate. At temperatures below 80 K, it forms a violet-black solid. most people can detect about 0.01 I/1 quarter mole per mole of ozone in air where it has a very specific sharp odor somewhat resembling chlorine bleach. Exposure of 0.1 to 1 I/1 quarter mole per mole produces headaches, burning eyes and irritation to the respiratory passages. Even low concentrations of ozone in air are very destructive to organic materials such as latex, plastics and animal lung tissue. Ozone is diamagnetic, which means that its electrons are all paired. In contrast, O2 is paramagnetic, containing two unpaired electrons. Structure: according to experimental evidence from microwave spectroscopy, ozone is a bent molecule, with C2V symmetry. The OA/O distances are 127.2 pm. The OA/OA/O angle is 116.78 degree. The central atom is sparse-squared hybridized with one lone pair. Ozone is a polar molecule with a dipole moment of 0.53 d. The bonding can be expressed as a resonance hybrid with a single bond on one side and double bond on the other, producing an overall bond order of 1.5 for each side. Reactions: ozone is a powerful oxidizing agent, far stronger than O2. It is also unstable at high concentrations, decaying to ordinary diatomic oxygen. It has a varying length half-life, depending upon atmospheric conditions. In a sealed chamber, with fan moving the gas, ozone has a half-life of approximately a day at room temperature. Some claims have been stated that ozone can have a half-life as short as a half an hour in atmospheric conditions, although this claim is not verified by this reference, 2O3O3O2. This reaction proceeds more rapidly with increasing temperature and increased pressure. Deflagration of ozone can be triggered by a spark, and can occur in ozone concentrations of 10 Wt% or higher. With metals, ozone will oxidize most metals to oxides of the metals in their highest oxidation state. For example, 2Cu++ 2 hours, 3O++O, 3O2Cu2++ 3 hours, 2O+O, 2, with nitrogen and carbon compounds. Ozone also oxidizes nitric oxide to nitrogen dioxide, NO+O, 3NO, 2+O, 2. This reaction is accompanied by chemiluminescence. The NO2 can be further oxidized, NO, 2+O, 3ONO3+O, 2. The number 3 formed can react with NO2 to form N2O, 5. Solid nitronium perchlorate can be made from NO2, ClO2, and O3 gases, 2NO, 2 plus 2 ClO2 plus 2O, 3O2NO2 ClO4 plus O2. Ozone does not react with ammonium salts, but it oxidizes ammonia to ammonium nitrate, 2NH, 3 plus 4O, 3NH, 4NO, 3 plus 4O, 2 plus H. 2O. Ozone reacts with carbon to form carbon dioxide, even at room temperature, C plus 2O3 or CO2 plus 2O2, with sulfur compounds. Ozone oxidizes sulfides to sulfates. For example, lead 2 sulfide is oxidized to lead 2 sulfate, PbS plus 4O3 or PbSO4 plus 4O2. Sulfuric acid can be produced from ozone, water and either elemental sulfur or sulfur dioxide, S plus H2O plus O3 or H2SO4, 3SO2 plus 3 hours 2O plus O3 or 3 hours 2SO4. In the gas phase, ozone reacts with hydrogen sulfide to form sulfur dioxide, H2S plus O3 or SO2 plus H2O, in an aqueous solution. However, 2 competing simultaneous reactions occur, one to produce elemental sulfur, and one to produce sulfuric acid, H2S plus O3OS plus O2 plus H2O, 3 hours 2S plus 4O3 or 3 hours 2SO4, with alkanes and alkanes. Alkanes can be oxidatively cleaved by ozone, in a process called ozonolysis, giving alcohols, aldehydes, ketones, and carboxylic acids, depending on the second step of the workup. Usually ozonolysis is carried out in a solution of dichloromethane, at a temperature of 78 oC. After a sequence of cleavage and rearrangement, an organic ozonide is formed. With reductive workup, ketones and aldehydes will be formed. With oxidative workup, carboxylic acids will be formed. Other substrates, all three atoms of ozone may also react, as in the reaction of tin, 2, chloride with hydrochloric acid and ozone, 3SnCl2 plus 6HCl plus O, 3SnCl4 plus 3 hours 2O. Iodine perchlorate can be made by treating iodine dissolved in cold anhydrous perchloric acid with ozone, I2 plus 6HClO4 plus O3 2I, ClO4, 3 plus 3 hours 2O. Combustion. Ozone can be used for combustion reactions and combusting gases. Ozone provides higher temperatures than combusting in dioxygen. The following is a reaction for the combustion of carbon subnitride which can also cause higher temperatures, 3 Celsius, 4N, 2 plus 4O, 3 12CO plus 3N, 2. Ozone can react at cryogenic temperatures. At 77 K, atomic hydrogen reacts with liquid ozone to form a hydrogen superoxide radical, which dimerizes, H plus O, 3HO2 plus O, 2HO2H, 2O, 4. Reduction to ozonides. Reduction of ozone gives the ozonide anion, O, 3. Derivatives of this anion are explosive and must be stored at cryogenic temperatures. Ozonides for all the alkali metals are known. KO3, RbO3, and CSO3 can be prepared from their respective superoxides, KO2 plus O3 or KO3 plus O2, although KO3 can be formed as above, it can also be formed from potassium hydroxide and ozone, 2KOH plus 5O3 or 2KO3 plus 5O2 plus H2O. NaO3 and LiO3 must be prepared by action of CSO3 and liquid NH3 on an ion exchange resin containing Na plus or Li plus ions, CSO3 plus Na plus or CS++. NaO3, a solution of calcium in ammonia reacts with ozone to give to ammonium ozonide and not calcium ozonide, 3Ca plus 10NH3 plus 6O, 3A 6 NH3 plus Ca, OH, 2 plus Ca. NO3, 2 plus 2NH4O3 plus 2O2 plus H2. Applications. Ozone can be used to remove manganese from water, forming a precipitate which can be filtered, 2Mn2 plus 2O, 3 plus 4 hours 2OA2MnO, OH, 2 plus 2O2 plus 4 hours plus. Ozone will also detoxify cyanides by converting them to cyanates, which are 1,000 times less toxic. Cna plus O3 or Cna plus O2, ozone will also completely decompose urea, NH2, 2CO plus O3 N2 plus CO2 plus 2 hours 2O, ozone in Earth's atmosphere. The standard way to express total ozone levels in the atmosphere is by using Dobson units. Point measurements are reported as mole fractions in mol or as concentrations in I1/4 gram per meter 3. The study of ozone concentration in the atmosphere started in the 1920s. Ozone layer. Location and production. The highest levels of ozone in the atmosphere are in the stratosphere, in a region also known as the ozone layer between about 10 km and 50 km above the surface. However, even in this layer the ozone concentrations are only 2 to 8 parts per million, so most of the oxygen there remains of the dioxygen type. Ozone in the stratosphere is mostly produced from shortwave ultraviolet rays, but it can be also produced from X-rays reacting with oxygen, O, 2 plus photon or 2O, O plus O, 2 plus MiO, 3 plus M, I plus or minus plus I squared or plus O, 2 He plus O, 3, where M denotes the third body that carries off the excess energy of the reaction. The thus produced ozone is destroyed by the reaction with atomic oxygen, O, 3 plus OA2O, 2, the latter reaction is catalyzed by the presence of certain free radicals, of which the most important are hydroxyl, nitric oxide and atomic chlorine and bromine. In recent decades the amount of ozone in the stratosphere has been declining mostly because of emissions of chlorofluorocarbons and similar chlorinated and brominated organic molecules, which have increased the concentration of ozone-depleting catalysts above the natural background. Importance to surface-dwelling life on Earth. Ozone in the ozone layer filters out sunlight wavelengths from about 200 nm UV rays to 315 nm, with ozone peak absorption at about 250 nm. This ozone UV absorption is important to life, since it extends the absorption of UV by ordinary oxygen and nitrogen in air through the lower UVC and the entire UVB band. The small unabsorbed part that remains of UVB after passage through ozone causes sunburn in humans, and direct DNA damage in living tissues in both plants and animals. Ozone's effect on mid-range UVB rays is illustrated by its effect on UVB at 290 nm, which has a radiation intensity 350 million times as powerful at the top of the atmosphere as at the surface. Nevertheless, enough of UVB radiation at similar frequency reaches the ground to cause some sunburn, and these same wavelengths are also among those responsible for the production of vitamin D in humans. The ozone layer has little effect on the longer UV wavelengths called UVA, but this radiation does not cause sunburn or direct DNA damage, and while it probably does cause long-term skin damage in certain humans, it is not as dangerous to plants and to the health of surface-dwelling organisms on Earth in general. Low-level ozone. Low-level ozone is an atmospheric pollutant. It is not emitted directly by car engines or by industrial operations, but formed by the reaction of sunlight on air containing hydrocarbons and nitrogen oxides that react to form ozone directly at the source of the pollution or many kilometers downwind. Ozone reacts directly with some hydrocarbons such as aldehydes and thus begins their removal from the air, but the products are themselves key components of smog. Ozone photolysis by UV light leads to production of the hydroxyl radical HO, and this plays a part in the removal of hydrocarbons from the air, but is also the first step in the creation of components of smog such as peroxyacyl nitrates, which can be powerful irritants. The atmospheric lifetime of tropospheric ozone is about 22 days. Its main removal mechanisms are being deposited to the ground, the above-mentioned reaction giving HO, and by reactions with OH and the peroxy radical HO2 a. There is evidence of significant reduction in agricultural yields because of increased ground-level ozone and pollution which interferes with photosynthesis and stunts overall growth of some plant species. The United States Environmental Protection Agency is proposing a secondary regulation to reduce crop damage, in addition to the primary regulation designed for the protection of human health. Certain examples of cities with elevated ozone readings are Houston, Texas, and Mexico City, Mexico. Houston has a reading of around 41 mmol, while Mexico City is far more hazardous, with a reading of about 125 mmol. Ozone cracking. Ozone gas attacks any polymer possessing olefinic or double bonds within its chain structure, such as natural rubber, nitrile rubber, and styrene butadiene rubber. Products made using these polymers are especially susceptible to attack, which causes cracks to grow longer and deeper with time, the rate of crack growth depending on the load carried by the rubber component and the concentration of ozone in the atmosphere. Such materials can be protected by adding anti-ozonants, such as waxes, which bond to the surface to create a protective film or blend with the material and provide long-term protection. Ozone cracking used to be a serious problem in car tires for example, but the problem is now seen only in very old tires. On the other hand, many critical products like gaskets and O-rings may be attacked by ozone produced within compressed air systems. Fuel lines made of reinforced rubber are also susceptible to attack, especially within the engine compartment, where some ozone is produced by electrical components. Storing rubber products in close proximity to a DC electric motor can accelerate ozone cracking. The commutator of the motor creates sparks which in turn produce ozone. Ozone is a greenhouse gas. Although ozone was present at ground level before the Industrial Revolution, peak concentrations are now far higher than the pre-industrial levels, and even background concentrations well away from sources of pollution are substantially higher. Ozone acts as a greenhouse gas, absorbing some of the infrared energy emitted by the Earth. Quantifying the greenhouse gas potency of ozone is difficult because it is not present in uniform concentrations across the globe. However, the most widely accepted scientific assessments relating to climate change suggest that the radiative forcing of tropospheric ozone is about 25% that of carbon dioxide. The annual global warming potential of tropospheric ozone is between 918 euro 1022 tons carbon dioxide equivalent tons tropospheric ozone. This means on a per molecule basis, ozone in the troposphere has a radiative forcing effect roughly 1,000 times as strong as carbon dioxide. However, tropospheric ozone is a short-lived greenhouse gas, which decays in the atmosphere much more quickly than carbon dioxide. This means that over a 20-year horizon, the global warming potential of tropospheric ozone is much less, roughly 62 to 69 tons carbon dioxide equivalent / tons tropospheric ozone. Because of its short-lived nature, tropospheric ozone does not have strong global effects, but has very strong radiative forcing effects on regional scales. In fact, there are regions of the world where tropospheric ozone has a radiative forcing up to 150% of carbon dioxide. Health effects. Ozone air pollution. Ozone precursors are a group of pollutants, predominantly those emitted during the combustion of fossil fuels. Ground-level ozone pollution is created near the Earth's surface by the action of daylight UV rays on these precursors. The ozone at ground level is primarily from fossil fuel precursors, but methane is a natural precursor, and the very low natural background level of ozone at ground level is considered safe. This section examines health impacts of fossil fuel burning, which raises ground-level ozone far above background levels. There is a great deal of evidence to show that ground-level ozone can harm lung function and irritate the respiratory system. Exposure to ozone and the pollutants that produce it is linked to premature death, asthma, bronchitis, heart attack, and other cardiopulmonary problems. Long-term exposure to ozone has been shown to increase risk of death from respiratory illness. A study of 450,000 people living in United States cities showed a significant correlation between ozone levels and respiratory illness over the 18-year follow-up period. The study revealed that people living in cities with high ozone levels such as Houston or Los Angeles had an over 30% increased risk of dying from lung disease. Air quality guidelines such as those from the World Health Organization, the United States Environmental Protection Agency and the European Union are based on detailed studies designed to identify the levels that can cause measurable ill health effects. According to scientists with the US EPA, susceptible people can be adversely affected by ozone levels as low as 40 mmol. In the EU, the current target value for ozone concentrations is 120 AA microgram mar cubed, which is about 16 mmol. This target applies to all member states in accordance with Directive 2000/80/EC. Ozone concentration is measured as a maximum daily mean of 8-hour averages, and the target should not be exceeded on more than 25 calendar days per year, starting from January 2010. Whilst the directive requires in the future a strict compliance with 120 AA microgram mar cube limit, there is no date set for this requirement, and this is treated as a long-term objective. In the USA, the Clean Air Act directs the EPA to set national ambient air quality standards for several pollutants, including ground-level ozone, and counties out of compliance with these standards are required to take steps to reduce their levels. In May 2008, under a court order, the EPA lowered its ozone standard from 80 mmol to 75 mmol. The move proved controversial, since the agency's own scientists and advisory board had recommended lowering the standard to 16 mmol. Many public health and environmental groups also supported the 16 mmol standard, and the World Health Organization recommends 51 mmol. On January 7, 2010, the U.S. Environmental Protection Agency announced proposed revisions to the National Ambient Air Quality Standard for the pollutant ozone, the principal component of smog. EPA proposes that the level of the 8-hour primary standard, which was set at 0.075 I1/4 mol per mole in the 2008 final rule, should instead be set at a lower level within the range of 0.060 to 0.070 I1/4 mol per mole, to provide increased protection for children and other at-risk unregistered trademark populations against an array of O3 related adverse health effects that range from decreased lung function. and increased respiratory symptoms to serious indicators of respiratory morbidity including emergency department visits and hospital admissions for respiratory causes, and possibly cardiovascular-related morbidity as well as total non-accidental and cardiopulmonary mortality. The EPA has developed an air quality index to help explain air pollution levels to the general public. Under the current standards, 8-hour average ozone mole fractions of 85 to 104 mmol are described as unhealthy for sensitive groups, 105 mmol to 124 mmol as unhealthy, and 125 mmol to 404 mmol as very unhealthy. Ozone can also be present in indoor air pollution, partly as a result of electronic equipment such as photocopiers. A connection has also been known to exist between the increased pollen, fungal spores, and ozone caused by thunderstorms and hospital admissions of asthma sufferers. In the Victorian era, one British folk myth held that the smell of the sea was caused by ozone. In fact, the characteristic smell of the sea is caused by dimethyl sulfide, a chemical generated by phytoplankton. Victorian British folk considered the resulting smell bracing, but in high concentrations, dimethyl sulfide is actually toxic. Heat waves. Ozone production rises during heat waves, because plants absorb less ozone. It is estimated that curtailed ozone absorption by plants is responsible for the loss of 460 lives in the UK in the hot summer of 2006. A similar investigation to assess the joint effects of ozone and heat during the European heat waves in 2003, concluded that these appear to be additive. Physiology. Ozone, along with reactive forms of oxygen such as superoxide, singlet oxygen, hydrogen peroxide, and hypochlorite ions, is naturally produced by white blood cells and other biological systems as a means of destroying foreign bodies. Ozone reacts directly with organic double bonds. Also, when ozone breaks down to dioxygen, it gives rise to oxygen-free radicals, which are highly reactive and capable of damaging many organic molecules. Moreover, it is believed that the powerful oxidizing properties of ozone may be a contributing factor of inflammation. The cause and effect relationship of how the ozone is created in the body and what it does is still under consideration and still subject to various interpretations, since other body chemical processes can trigger some of the same reactions. A team headed by Dr. Paul Wentworth Jr. of the Department of Chemistry at the Scripps Research Institute has shown evidence linking the antibody-catalyzed water oxidation pathway of the human immune response to the production of ozone. In this system, ozone is produced by antibody-catalyzed production of trioxidane from water and neutrophil-produced singlet oxygen. When inhaled, ozone reacts with compounds lining the lungs to form specific, cholesterol-derived metabolites that are thought to facilitate the buildup and pathogenesis of atherosclerotic plaques. These metabolites have been confirmed as naturally occurring in human atherosclerotic arteries and are categorized into a class of secosterols termed atherinols, generated by ozonolysis of cholesterol's double bond to form a 5,6-secosterol as well as a secondary condensation product via aldolization. Ozone has been implicated to have an adverse effect on plant growth. Ozone reduced total chlorophylls, carotenoid and carbohydrate concentration, and increased 1-aminocyclopropane 1-carboxylic acid content and ethylene production. In treated plants, the ascorbate leaf pool was decreased, while lipid peroxidation and solute leakage were significantly higher than in ozone-free controls. The data indicated that ozone triggered protective mechanisms against oxidative stress in citrus. Safety regulations. Due to the strongly oxidizing properties of ozone, ozone is a primary irritant, affecting especially the eyes and respiratory systems and can be hazardous at even low concentrations. The Canadian Centre for Occupation Safety and Health reports that even very low concentrations of ozone can be harmful to the upper respiratory tract and the lungs. The severity of injury depends on both by the concentration of ozone and the duration of exposure. Severe and permanent lung injury or death could result from even a very short-term exposure to relatively low concentrations. To protect workers potentially exposed to ozone, U.S. Occupational Safety and Health Administration has established a permissible exposure limit of 0.1 I/1/4 mol per mole. calculated as an 8-hour time-weighted average. Higher concentrations are especially hazardous, and NIOSH has established an immediately dangerous to life and health limit of 5 I1/4 mol per mole. Work environments where ozone is used or where it is likely to be produced should have adequate ventilation, and it is prudent to have a monitor for ozone that will alarm if the concentration exceeds the OSHAPEL. Continuous monitors for ozone are available from several suppliers. Elevated ozone exposure can occur on passenger aircraft, with levels depending on altitude and atmospheric turbulence. United States Federal Aviation Authority regulations set a limit of 250 mmol with a maximum 4-hour average of 100 mmol. Some planes are equipped with ozone converters in the ventilation system to reduce passenger exposure. Production: ozone often forms in nature under conditions where O2 will not react. Ozone used in industry is measured in I1/4 mol per mole, mol, I1/4 gram per meter 3, milligram per hour or weight percent. The regime of applied concentrations ranges from 1 to 5% in air and from 6 to 14% in oxygen for older generation methods. New electrolytic methods can achieve up 20 to 30% dissolved ozone concentrations in output water. Temperature and humidity plays a large role in how much ozone is being produced using traditional generation methods such as corona discharge and ultraviolet light. Old generation methods will produce less than 50% its nominal capacity if operated with humid ambient air than when it operates in very dry air. New generators using electrolytic methods can achieve higher purity and dissolution through using water molecules as the source of ozone production. Corona discharge method: this is the most common type of ozone generator for most industrial and personal uses. While variations of the hot spark coronal discharge method of ozone production exist, including medical-grade and industrial-grade ozone generators, these units usually work by means of a corona discharge tube. They are typically cost-effective and do not require an oxygen source other than the ambient air to produce ozone concentrations of 3–6%. Fluctuations in ambient air, due to weather or other environmental conditions, cause variability in ozone production. However, they also produce nitrogen oxides as a byproduct. Use of an air dryer can reduce or eliminate nitric acid formation by removing water vapor and increase ozone production. Use of an oxygen concentrator can further increase the ozone production and further reduce the risk of nitric acid formation by removing not only the water vapor, but also the bulk of the nitrogen. Ultraviolet light, UV ozone generators, or vacuum ultraviolet ozone generators, employ a light source that generates a narrow-band ultraviolet light, a subset of that produced by the sun. The sun's UV sustains the ozone layer in the stratosphere of Earth. While standard UV ozone generators tend to be less expensive, they usually produce ozone with a concentration of about 0.5% or lower. Another disadvantage of this method is that it requires the air to be exposed to the UV source for a longer amount of time, and any gas that is not exposed to the UV source will not be treated. This makes UV generators impractical for use in situations that deal with rapidly moving air or water streams. Production of ozone is one of the potential dangers of ultraviolet germicidal irradiation. VUV ozone generators are used in swimming pool and spa applications ranging to millions of gallons of water. VUV ozone generators, unlike corona discharge generators, do not produce harmful nitrogen byproducts, and also unlike corona discharge systems, VUV ozone generators work extremely well in humid air environments. There is also not normally a need for expensive off-gas mechanisms, and no need for air dryers or oxygen concentrators which require extra costs and maintenance. Cold plasma: in the cold plasma method, pure oxygen gas is exposed to a plasma created by dielectric barrier discharge. The diatomic oxygen is split into single atoms, which then recombine in triplets to form ozone. Cold plasma machines utilize pure oxygen as the input source and produce a maximum concentration of about 5% ozone. They produce far greater quantities of ozone in a given space of time compared to ultraviolet production. However, because cold plasma ozone generators are very expensive, they are found less frequently than the previous two types, the discharge is manifest as filamentary transfer of electrons in a gap between two electrodes. In order to evenly distribute the microdischarges, a dielectric insulator must be used to separate the metallic electrodes and to prevent arcing. Some cold plasma units also have the capability of producing short-lived allotropes of oxygen which include O4, O5, O6, O7, etc. These species are even more reactive than ordinary O3. Electrolytic ozone generation splits water molecules into H2, O2, and O3. In most EOG methods, the hydrogen gas will be removed to leave oxygen and ozone as the only reaction products. Therefore, EOG can achieve higher dissolution in water without other competing gases found in corona discharge method, such as nitrogen gases present in ambient air. This method of generation can achieve concentrations of 20–30% and is independent of air quality because water is used as the source material. Production of ozone electrolytically is typically unfavorable because of the high overpotential required to produce ozone as compared to oxygen. This is why ozone is not produced during typical water electrolyses. However, it is possible to increase the overpotential of oxygen by careful catalyst selection such that ozone is preferentially produced under electrolyses. Catalysts typically chosen for this approach are lead dioxide or boron-doped diamond. Special considerations: ozone cannot be stored and transported like other industrial gases and must therefore be produced on site. Available ozone generators vary in the arrangement and design of the high-voltage electrodes. At production capacities higher than 20 kg per hour, a gas-water tube heat exchanger may be utilized as ground electrode and assembled with tubular high-voltage electrodes on the gas side. The regime of typical gas pressures is around 2 bars absolute in oxygen and 3 bars absolute in air. Several megawatts of electrical power may be installed in large facilities, applied as one-phase AC current at 50 to 8000 Hz and peak voltages between 3000 and 20,000 volts. Applied voltage is usually inversely related to the applied frequency. The dominating parameter influencing ozone generation efficiency is the gas temperature, which is controlled by cooling water temperature and/or gas velocity. The cooler the water, the better the ozone synthesis. The lower the gas velocity, the higher the concentration. At typical industrial conditions, almost 90% of the effective power is dissipated as heat and needs to be removed by a sufficient cooling water flow. Because of the high reactivity of ozone, only a few materials may be used like stainless steel, titanium, aluminium, glass, polytetrafluoroethylene, or polyvinylidene fluoride. Viton may be used with the restriction of constant mechanical forces and absence of humidity. Hypalon may be used with the restriction that no water come in contact with it, except for normal atmospheric levels. Embrittlement or shrinkage is the common mode of failure of elastomers with exposure to ozone. Ozone cracking is the common mode of failure of elastomer seals like O-rings. Silicone rubbers are usually adequate for use as gaskets in ozone concentrations below 1 Wt%, such as in equipment for accelerated aging of rubber samples. Incidental production: ozone may be formed from O2 by electrical discharges and by action of high-energy electromagnetic radiation. Unsuppressed arcing breaks down the chemical bonds of the atmospheric oxygen surrounding the contacts, O2 or 2O. Free radicals of oxygen in and around the arc recombine to create ozone, O3. Certain electrical equipment generates significant levels of ozone. This is especially true of devices using high voltages, such as ionic air purifiers, laser printers, photocopiers, tasers and arc welders. Electric motors using brushes can generate ozone from repeated sparking inside the unit. Large motors that use brushes, such as those used by elevators or hydraulic pumps, will generate more ozone than smaller motors. Ozone is similarly formed in the Catatumbo lightning storms phenomenon in the Catatumbo River in Venezuela, which helps to replenish ozone in the upper troposphere. It is the world's largest single natural generator of ozone, lending calls for it to be designated a UNESCO World Heritage Site. Laboratory production: in the laboratory, ozone can be produced by electrolysis using a 9-volt battery, a pencil graphite rod cathode, a platinum wire anode and a 3-molar sulfuric acid electrolyte. The half-cell reactions taking place are 3H2OO3 plus 6 hours plus 6A, 6 hours plus 6A are 3 hours 2 hours 2OO2 plus 4 hours plus 4A. In the net reaction, 3 equivalents of water are converted into 1 equivalent of ozone and 3 equivalents of hydrogen. Oxygen formation is a competing reaction. It can also be prepared by high-voltage arc. This can be done with an apparatus consisting of 2 concentric glass tubes sealed together at the top, with in and out spigots at the top and bottom of the outer tube. The inner core should have a length of metal foil inserted into it connected to one side of the power source. The other side of the power source should be connected to another piece of foil wrapped around the outer tube. Dry O2 should be run through the tube in one spigot. As the O2 is run through one spigot into the apparatus and high voltage is applied to the foil leads, electricity will discharge between the dry dioxygen in the middle and form O3 and O2 out the other spigot. The reaction can be summarized as follows: 3O2 electricity A2O3. Applications: Industry. The largest use of ozone is in the preparation of pharmaceuticals, synthetic lubricants, and many other commercially useful organic compounds, where it is used to sever carbon-carbon bonds. It can also be used for bleaching substances and for killing microorganisms in air and water sources. Many municipal drinking water systems kill bacteria with ozone instead of the more common chlorine. Ozone has a very high oxidation potential. Ozone does not form organochlorine compounds, nor does it remain in the water after treatment. Ozone can form the suspected carcinogen bromate in source water with high bromide concentrations. The Safe Drinking Water Act mandates that these systems introduce an amount of chlorine to maintain a minimum of 0.2 I mole per mole residual-free chlorine in the pipes, based on results of regular testing. Where electrical power is abundant, ozone is a cost-effective method of treating water, since it is produced on demand and does not require transportation and storage of hazardous chemicals. Once it has decayed, it leaves no taste or odor in drinking water. Although low levels of ozone have been advertised to be of some disinfectant use in residential homes, the concentration of ozone in dry air required to have a rapid, substantial effect on airborne pathogens exceeds safe levels recommended by the U.S. Occupational Safety and Health Administration and Environmental Protection Agency. Humidity control can vastly improve both the killing power of the ozone and the rate at which it decays back to oxygen. Spore forms of most pathogens are very tolerant of atmospheric ozone in concentrations where asthma patients start to have issues. Industrially, ozone is used to disinfect laundry in hospitals, food factories, care homes etc. Disinfect water in place of chlorine, deodorize air and objects, such as after a fire. This process is extensively used in fabric restoration, kill bacteria on food or on contact surfaces. Sanitize swimming pools and spas, kill insects in stored grain, scrub yeast and mold spores from the air in food processing plants. Wash fresh fruits and vegetables to kill yeast, mold and bacteria. Chemically attack contaminants in water. Provide an aid to flocculation. Manufacture chemical compounds via chemical synthesis, clean and bleach fabrics. Assist in processing plastics to allow adhesion of inks. Aid rubber samples to determine the useful life of a batch of rubber. Eradicate waterborne parasites such as Giardia lamblia and Cryptosporidium in surface water treatment plants. Ozone is a reagent in many organic reactions in the laboratory and in industry. Ozonolysis is the cleavage of an alkane to carbonyl compounds. Many hospitals around the world use large ozone generators to decontaminate operating rooms between surgeries. The rooms are cleaned and then sealed airtight before being filled with ozone, which effectively kills or neutralizes all remaining bacteria. Ozone is used as an alternative to chlorine or chlorine dioxide in the bleaching of wood pulp. It is often used in conjunction with oxygen and hydrogen peroxide to eliminate the need for chlorine-containing compounds in the manufacture of high-quality, white paper. Ozone can be used to detoxify cyanide wastes by oxidizing cyanide to cyanate and eventually to carbon dioxide. Consumers, devices generating high levels of ozone, some of which use ionization, are used to sanitize and deodorize uninhabited buildings, rooms, ductwork, woodsheds, and boats and other vehicles. One company has been successfully selling a CPAP sanitizer for the CPAP gear used by sleep apnea patients. This sanitizer works by pumping high concentration levels of electrically generated ozone into the unit's humidification water tank and out through the hose into the mask, which is enclosed and sealed in an ozone-capturing receptacle, which completes a closed-loop system. This closed-loop system prevents the high levels of ozone from escaping while effectively sanitizing the CPAP equipment, as the CPAP equipment is prone to developing bacterial infestations and harboring viruses and other pathogens because of the constant moisture generated by the CPAP system's humidifier. The sanitizing unit has a 2-hour cycle. It pumps the ozone for 6 to 10 minutes and then resting for 2 hours while maintaining the sealed closed-circuit loop as the ozone decays back into oxygen and finishes the sanitizing effect. In the U.S., air purifiers emitting low levels of ozone have been sold. This kind of air purifier is sometimes claimed to imitate nature's way of purifying the air without filters and to sanitize both it and household surfaces. The United States Environmental Protection Agency has declared that there is evidence to show that at concentrations that do not exceed public health standards, ozone is not effective at removing many odor-causing chemicals, or viruses, bacteria, mold, or other biological pollutants. Furthermore, its report states that results of some controlled studies show that concentrations of ozone considerably higher than these human safety standards are possible even when a user follows the manufacturer Euro unregistered trademark S operating instructions. A couple kept repeating health claims for the generator they sold, without supporting scientific studies. In 1998 a federal jury convicted them, among other things, of illegally distributing an ozone generator and of wire fraud. Ozonated water is used to launder clothes and to sanitize food, drinking water, and surfaces in the home. According to the U.S. Food and Drug Administration, it is amending the food additive regulations to provide for the safe use of ozone in gaseous and aqueous phases as an antimicrobial agent on food, including meat and poultry. Studies at California Polytechnic University demonstrated that 0.301 quarter mole per mole levels of ozone dissolved in filtered tap water can produce a reduction of more than 99.99% in such food-borne microorganisms as Salmonella, E. coli 0157, H7 and Campylobacter. This quantity is 20,000 times the WHO recommended limit stated above. Ozone can be used to remove pesticide residues from fruits and vegetables. Ozone is used in homes and hot tubs to kill bacteria in the water and to reduce the amount of chlorine or bromine required by reactivating them to their free state. Since ozone does not remain in the water long enough, ozone by itself is ineffective at preventing cross-contamination among bathers and must be used in conjunction with halogens. Gaseous ozone created by ultraviolet light or by corona discharge is injected into the water. Ozone is also widely used in treatment of water in aquariums and fish ponds. Its use can minimize bacterial growth, control parasites, eliminate transmission of some diseases, and reduce or eliminate yellowing of the water. Ozone must not come in contact with fish's gill structures. Natural salt water provides enough instantaneous demand that controlled amounts of ozone activate bromide ion to hypobromous acid, and the ozone entirely decays in a few seconds to minutes. If oxygen-fed ozone is used, the water will be higher in dissolved oxygen, fish's gill structures will atrophy and they will become dependent on higher dissolved oxygen levels. Aquaculture, ozonation, a process of infusing water with ozone, can be used in aquaculture to facilitate organic breakdown. Ozone is also added to recirculating systems to reduce nitrite levels through conversion into nitrate. If nitrite levels in the water are high, nitrites will also accumulate in the blood and tissues of fish, where it interferes with oxygen transport to ferric, making hemoglobin unable to bind O2. Despite these apparent positive effects, Ozone use in recirculation systems has been linked to reducing the level of bioavailable iodine in saltwater systems, resulting in iodine deficiency symptoms such as goiter and decreased growth in Senegalese sole larvae. Ozonate seawater is used for surface disinfection of haddock and Atlantic halibut eggs against nodavirus. Nodavirus is a lethal and vertically transmitted virus which causes severe mortality in fish. Haddock eggs should not be treated with high ozone level as eggs so treated did not hatch and died after 3–4 days. Agriculture. Ozone application on freshly cut pineapple and banana shows increase in flavonoids and total phenol contents when exposure is up to 20 minutes. Decrease in ascorbic acid content is observed, but the positive effect on total phenol content and flavonoids can overcome the negative effect. Tomatoes upon treatment with ozone shows an increase in I-squared carotene, lutein and lycopene. However, ozone application on strawberries in pre-harvest period shows decrease in ascorbic acid content. Ozone facilitates the extraction of some heavy metals from soil using EDTA. EDTA forms strong, water-soluble coordination compounds with some heavy metals, thereby making it possible to dissolve them out from contaminated soil. If contaminated soil is pre-treated with ozone, the extraction efficacy of Pb, Am and Pu increases by 11.0 28.9%, 43.5% and 50.7% respectively. See also, cyclic ozone, global ozone monitoring by occultation of stars, greenhouse gas, International Day for the Preservation of the Ozone Layer, nitrogen oxides, Ozone Action Day, ozone depletion, including the phenomenon known as the ozone hole. Ozone therapy, ozone web, ozonolysis, polymer degradation, references. Further reading, Greenwood, Norman N. Earnshaw, Alan. Chemistry of the Elements. Butterworth Heinemann. ISBN 0080379419 series in plasma physics, non-equilibrium air plasmas at atmospheric pressure. Edited by K. H. Becker, Ukagels Charts, K. H. Schoenbach, R. J. Barker. Bristol and Philadelphia, Institute of Physics Publishing Limited. ISBN 0-7503-0962-8. 2005, External links, International Ozone Association, European Environment Agency's Near Real-Time Ozone Map, NASA's Ozone Resource Page, OSHA Ozone Information, Paul Crutzen interview. Freeview video of Paul Crutzen, Nobel laureate for his work on decomposition of ozone, talking to Harry Kroto, Nobel laureate by the Vega Science Trust. NASA's Earth Observatory article on ozone, International Chemical Safety Card 0068, NIOSH Pocket Guide to Chemical Hazards, National Institute of Environmental Health Sciences, Ozone Information, Ground-level ozone air pollution, NASA study links smog to Arctic warming. NASA Goddard Institute for Space Studies study shows the warming effect of ozone in the Arctic during winter and spring. RCPA report questioning effectiveness or safety of ozone generators sold as air cleaners, pesticides database. Ozone, ground-level ozone information from the American Lung Association of New England.